because we're actually jumping into proving your first geometric facts. Again, this class is all about facts, and started with Euclid with proving the original kind of geometric facts and sort of the foundation of Western geometry and philosophy and fact finding, really, and influenced people in the 1900s. Of course, Abraham Lincoln, will be talking more about him, and continues to influence people who care quite a bit about facts in today's day and age. Because I just got off of Facebook arguing with people who just, where do you get your facts from? Ridiculous. All right, so we're jumping into it. We got here the agenda of today. So your first geometric proofs is the topic of today's class. You're going to use the 8 properties from algebra you learned on Monday. Okay, so we'll use those today. Also, most definitions you've used so far, postulates, and the 3 properties of congruency below. This is sort of telling you what is in the first geometric proofs that you'll do this year. So really the main thing that we're going to do at the beginning is talk about these properties of congruence, because along with everything else you've learned so far, the postulates and properties from algebra and definitions in geometry as well, these will be used along with those in proofs of geometric theorems. And so these proofs here are going to look kind of similar to the ones you did on algebra on Monday, in terms that it'll have 2 columns. So hopefully you remember those proofs, 2 columns. You had statements on one side and reasons on the other. And your reasons are going to be all this stuff, right? These properties of congruence we see here, and the properties from algebra from Monday and whatnot here. All right, so agenda, what we're going to do today is we're going to talk about each of the 3 properties of congruency now. We're going to talk about these 3 things here: the reflexive property of congruence, the symmetric property of congruence, and the transitive property of congruence. These should look a little familiar because they're also properties of equality. So that's what we're going to do first. Second thing that we're going to do in this lesson is we're going to practice telling the difference between the 3 of these. When is it a reflexive property of congruence? When is it symmetric? And when is it transitive? That'll be important to be able to distinguish the difference so we can actually prove things, right? And get some more interesting facts later this year. Thirdly, and last but certainly not least, we're actually going to practice using the properties of congruence, which we'll study right now, in proofs, right? Proving things. And we'll use the other reasons you've used before, right? So definitions and postulate, all that good stuff. And we're actually going to do what we did on Monday and Tuesday, right? Where we proved algebraically how to prove the solution to an equation. We're going to do that instead with shapes, instead with geometry. We start with some original assumptions about a problem. We can prove facts follow from that. That's what this class is all about. As Sal Khan said in the video this past weekend, geometry really is what math is all about, starting with assumptions. And from that, those basic assumptions, you deduced facts from them. Reminder, after we get done with this, complete your exit ticket afterwards. It'll be made available to you Wednesday afternoon, right? I give you a couple hours, right? So maybe you don't have time to watch the video right away. Watch the video early afternoon. It's available to you after that. So once you've completed the lesson, I kind of make that available to you guys here. Part 1 of today's lesson, so let's go ahead and on into it. We're going to discuss the 3 properties of congruence: the reflexive property, symmetric property, and transitive property. Please, please, please take notes on this. Just like on Monday, we learned all those properties from algebra, and you're realizing, I think it's some of you guys at your exit tickets, you said, oh, I got to really work on knowing the difference between these properties from algebra. It's certainly true. And the ones we're going to introduce today as well, you got to know the differences between these 3. So definitely take notes and just really look closely to what they say and how we can use them later this year. I'm going to go ahead and turn on the lights. I'll be right back. Now that you can see me better, we got our first property of congruence. This one's called the reflexive property of congruence. So we dealt with reflexive earlier on. Right? We dealt with reflexive on Monday. Reflexive was that with reflexive property of equality was that basically told us that any number equaled itself, right? Any number equals itself. We can say that about any number. Well, 5, what does 5 equal? 5 equals 5. So there's also a reflexive property of congruence because, like the properties of algebra, properties of congruence are also kind of assumptions, things that are completely obvious that we just accept them without proof. And obviously here we can accept these 2 statements without proof here. So if you ever say this in a proof, if you ever say this when you're trying to prove something else here, the reason why you can say DE is congruent to DE is because any shape has the reflexive property. So for instance, if we have a segment DE, and didn't mean to draw it like that. We have a segment DE, so I have a point here and a point here. That segment here, of course, is going to be just as long as itself. So it is congruent to itself. By definition, it has length DE, and that's just as long as length DE of itself. So DE is congruent to DE. And then finally, angle FGH is congruent to angle FGH, also a reflexive property of congruence. And this will become important because sometimes we need to show a certain number of angles are congruent, or a certain number of sides of a figure, of a triangle, for instance, are congruent to other sides of a triangle. So sometimes you need to use this if they share features and whatnot here. So just to summarize this right here, I got it down here, just kind of in diagrams. This here, DE is congruent to DE because its length, there's just one length. So we can say this thing is congruent to itself reflexively. And right, reflexively means you look back at yourself, right? The mirror reflects at me. So what I see in the mirror is kind of exactly the same as me. Not quite, obviously. It's not me. It's the man in the mirror. But anyways, that's the way you can remember it. Reflexive means just, well, what's itself? What's the thing there? What can we say about itself? Well, it's congruent to itself. Same thing here too is kind of demonstrating this assumption right here, that angle FGH. Well, that's going to have a certain amount of hinge to it, and how does that compare to itself? Well, it's the same hinge, and therefore, if it has the same angle measure, by definition, this angle would need to be congruent to itself. So again, we're not talking about two angles right here. We're just talking about one angle, but an angle can be congruent to itself. Moving on here, this one's not that important, but it's in your section right here, the symmetric property of congruence. Shapes can be proven congruence by the symmetric property. So what symmetric property means is here, remember in Algebra 1, you used to draw a line of symmetry right down here. Right, line of symmetry right down here. So symmetric property is the thing that tells us that the side of congruent symbol doesn't matter at all. Okay, so if you have an angle D right here, let's say it's like 30 degrees, and it's congruent to, we can say that the angle of 30 degrees is congruent to an angle E, that's also 30 degrees. If we make that angle D is congruent to angle E, we can also make the conclusion that angle E is congruent to angle D. That's totally legit here, right? If this thing's congruent to that thing, then that thing also is congruent to that thing. So this is sort of a silly one. It doesn't really come up very often, but this is the symmetric property. In that, what it does is it tells us that side of the congruent symbol does not matter. You guys remember the line of symmetry? Right, line of symmetry of a parabola, for instance, the left side look exactly as the right side. So symmetric property means that the sides, right, symmetrically, it doesn't matter where we put our congruent shapes, or which shapes we choose to say first. E is congruent to angle D is the same thing as angle D congruent to angle E. Doesn't really matter at all. Symmetric property doesn't come up much in proofs. Comes up kind of like in this section, just so you know that it's a property, but you don't really need to worry about it too much. So symmetric property of congruence, one way you can remember it. So similarly, reflexive property was any figure is congruent to itself. So what we can say about this here is that any figure that's congruent to another figure, right? Any figure congruent to another figure. Well, that other figure has got to be congruent to the original figure we started talking about here. And then, right, that's one way we can kind of put it informally in words. But the way that most people remember it is that the side of where the things appear in a congruency statement does not matter at all. Okay, does not matter at all. So if you remember this here, just quick reminders, when we have symbolically something written out like this here, remember, this is the hypothesis and that is the conclusion. So we read the symmetric property. If you're reading it in your book, they're going to write it like this. If, right, remember, this is the hypothesis. So if, the hypothesis is what's come out for the if angle D is congruent to angle E, and then here, right, this tells us that we're going to read this if then, that arrow right there. If angle D is congruent to angle E, then we can make the conclusion that angle E is congruent to angle D. If you ever need to do that, you're using the symmetric property to justify, right, as your reason to prove something else. You're not really going to have to worry about that. That's not going to come up too much. All right, here we go. Keep moving on here. Shapes can be proven congruent by the transitive property. So you studied the transitive property of equality on Monday. Go back and rewatch a bit of that if you kind of got a little bit confused. I caught a lot of people on the exit ticket because transitive property is oftentimes very much confused with the substitution property of equality. And part of that is you actually kind of study substitution and transitive property at the same time in Algebra 1 as well. So I'm really kind of going way back in Algebra 1. But at Algebra 1, you probably did something called the equal values method. Right? You didn't remember the equal values method. If you have me, I taught it to you. But anyways, equal values method is actually the transitive property. They call it equal values method in some of the Algebra 1 textbooks now. It's the transitive property. And then substitution was your other way that one of the other ways you solved the system. That was something different, right? Very similar, but something different. So transitive property is something where, and you remember transitive property is kind of the equal values method, actually. What do I mean by equal values? Well, check it out here. we got here angle Y mentioned here in two different statements of congruency right here. So what we can say about this is that if angle X is congruent to angle Y, and angle Y is congruent to angle Z, right? See here, angle Y equals two different things, right? Equals two different things. So what's the thing that we can deduce, or at least this is actually an agreement transitive property. Let's agree to something that we can proceed with math and actually make a statement based off of this. That's a brand new statement of congruency. What's the brand new statement of congruency that you think is super logical that you can jump to? Well, that is angle X is congruent to angle Z, right? It's that right there. So check it out here. I like to say that the transitive property deals with three things in two equations or two congruencies here, okay? That's the difference between it and substitution, is that transitive property is very specific. You have two equations and you have three things mentioned in those equations, or you have two statements of congruency and you have three shapes total talking about it. And there's one common thread. And what I mean by common thread is I mean angle Y, because angle Y is congruent to one thing, it's congruent to another thing. So what we can deduce about those two things that are congruent to, well, they got to kind of be the same thing. They got to be congruent to one another here. So the way that I remember transitive property, and I think I have this coming up a little later too, so maybe I can go over it a little bit faster here. Transitive is just like a triangle, right? TR. How many sides does a triangle have? A triangle has three sides. So check it out here. We got number one, right? Our first shape is congruent to a second shape. And then that second shape is congruent to a third shape. So if we know that we have these two statements in our given premise, if this, the conclusion we can make is, well, that and that, they're both congruent to the same thing. They are congruent to each other. So if we have, again, going back to that 30-degree example, if we have angle X right here, we have angle Y right here, right? And they're congruent to each other because they're 30-degree angles, right? So they're congruent. And let's say Y is congruent to another angle. Would that other angle being angle Z, what would that angle Z's measure have to be if Y is congruent to it? So Y is 30 degrees, and that would mean Z would have to be 30 degrees if it is in fact congruent to angle Y. So what we can make as our conclusion through this, the common thread right here, is that the two things that it's congruent to are congruent to each other. And this is coming back there from Euclid. We're going to talk about this. This actually is something that was all in Lincoln's business for a while, and I'll definitely talk about that for a little bit. Things that are the two things that are both equal to the same thing are equal to each other. Very powerful statement. I'm going to show you a very powerful clip on that pretty soon here. Anyways, transitive property, there it is, right? Written out symbolically for you here too. Definitely in your exit ticket, there's going to be something like this appearing. Transitive. Again, how many things are mentioned in transitive? You have one, you have two, that two thing gets repeated. We found a common thread. We can set 1 and 3 equal to each other, or 1 and 3 congruent to one another. Shorthand, here's how this has been said for thousands of years, since the time of Euclid here. If two figures are congruent to the same figure, and those two figures are congruent to each other. Put that in your notes, put the orange stuff in your notes. Symmetric property, reflexive property, put these orange things I'm putting down here, because that's, I think, the way that you're going to kind of memorize this stuff and remember it here. Continuing on, we're on slide 10. Hey, I like this pace we're going, because again, I'm going to try to go through these fast so you can just rewatch things that you think you need to rewatch. So summary, properties of congruence, and we got done with segment 1 of 3. Reflexive property, any figure is congruent to itself. Symmetric property, you can read this on your own time. You've written it down. Transitive property, you'll practice it later. I don't need to say it out loud here. Okay, the one you really need to memorize is the transitive property of congruence. And you need to understand the difference between that and substitution. That's the age-old geometry question, right? It takes a few months for some people to realize the difference. So really the thing to point out this time, so you're just like not like for weeks being like, I don't get it. How many shapes are talked about in the transitive property? We got 2 letters in caps there, TR. How many shapes are talked about in the transitive property at the beginning? How many total? I see 3. How many sides are there in a triangle? Also starts with the first 2 letters as the transitive property. So the TR thing kind of telling us 3, Triceratops 3, right? I think Triceratops has 3 things on the back. I don't know. It's been a while since I've studied dinosaurs. But anyways, here. So what we can deduce from this situation, FG equals these 2 things. So those 2 things got to be congruent to one another. I said equals. I meant to say congruence because this is the property of congruence here. Angle D is congruent to angle E. Angle E is congruent to angle F. And what we deduce is that angle D is congruent to angle F. If we know this, then we can do this. So one thing that I sort of differentiate it with the substitution property is you're actually technically building out a brand new equation. You're not substituting a segment DE in for FG right here. You can maybe make the argument that you're doing that, but no, a better reason, because this is actually the first thing. This is something called a common notion that Euclid wrote about in the Elements, and it's his very first common notion. Is that two things which are each equal to the same thing are equal to each other. Euclid didn't use the word congruent. There was some necessary stuff after Euclid to actually describe congruency versus equality. But so he said equal, but it's later emerged as the property of congruence. Anyways, we can talk all about that later. All right, part 2 of today's lesson. So now we're going to do some practice looking at geometric statements and determining which of the 3 properties of congruency and properties of equality would be the correct justification for each statement. So we're going to get some practice right now. You're going to kind of do it on your own. Normally, I do this as a group. And okay, so we're going to determine the difference, the 3 properties. So there's 3 things we just talked about. Make sure you're ready to practice them right now. What's the correct justification for all of these statements that we have right here? We'll practice section 1-4. Usually we do this with our group. I give you a minute or 2, and then we share out, right? Like picking names out of the hat, I like going around, like, all right, what'd you get for this? And it takes about 3 or 4 minutes to go through this, but I'm only giving you a minute and a half to look at this and categorize them. Then we'll go over it together here. So name the properties of equality. So notice here, right? Remember the 3 properties of congruence, this up here. If I just tell you reflexive, symmetric, or transitive, am I talking about properties of congruence, or am I talking about properties of equality, or do you not know? So remember, these 3 things are all properties of equality, right? Which is important if you're talking about numbers or lengths, right? Distances or angle measurements, you're going to use the property of equality. So that'll be confusing, something to look out for too. But if you're talking about the shapes themselves, then you use a property of congruence. What are we looking at down here? This here, what's KM? Is that a segment? Is that our line? What is that? Is KM a segment? No, it's a distance. It's a length, right? So remember, we have 2 letters next to one another. It means the distance between those 2 points, between KM. So if KM is equal to PQ, then PQ is equal to KM. So see here, our operator here is all equality, right? Our statements, these are all equations here. So these are properties of equality. Anyways, I've kind of gone on longer than I wanted to. I'm going to give you guys a minute or so to look at this, a little bit of peace and quiet, and then we'll talk about the answers. Ready, set, a go. What do you guys think of my new haircut? Don't mind me. "20 seconds, and then we'll go over them. See how you did. You can pause the video too. Anybody pick up a textbook this week? 5 seconds. 4, 3, 2, and 1. All right, let's see how you did, guys. Let's see how you did. Let's kind of go over it again. I'm picking the names out of the hat and calling out people. This first one here, well, hey, how many expressions do we see here? In the if statement, we have 2 equations, so that's sort of a hint there. 2 equations, how many expressions? We have an expression R, we have an expression S. S gets repeated right here. We have an expression T. That's got to be transitive, right? Transitive. So 2 things, R and T are equal to each other because they're both equal to S. So definitely transitive. But the key thing is here, 2 equations, 3 things being talked about. That's your cue. That's going to be the transitive property of equality. This one looks like symmetric, huh? Let's see. Let's get the answers down. We'll just talk about them here. So I got the answers right there. Transitive right here, symmetric right here. Yes, transitive here. It's a little bit tougher here. Notice here, this when I mean expressions. It's okay if it's. What I mean by expression, I mean everything that's on one side of an equal sign. Right, one side of an equal sign. So 180 is an expression, right? Because it's the entire side of an equal sign. A plus B here is the expression on the left side of the equal sign here. So the thing that gets repeated is the 180. Look, 180 here. So that means what we can deduce from this, if we know this is true in our hypothesis, A plus B equals 180 and M plus N equals 180, then we can deduce that this expression here because it equals 180, and this expression here because it equals 180, that they equal each other. That's the transitive property of equality. Reflexive here, symmetric here. Ooh, a little tricky there. That one was reflexive. Hopefully you got that one. So notice here, there was no if here. There was no if here. For reflexive, we don't need an if. We can just say, well, that's a figure. It's congruent to itself. Well, it's just a fact, right? It's not even really a rule. So I guess we call it a rule because we need the way to work around here. Okay. Anyways, just to show you how similar this is to the stuff you've been doing with the properties of equality here in section 1.4. We're just changing it up here to the properties of congruence. Check it out here, properties of congruence. So this is very, very similar problems here, reflexive, symmetric, or transitive. And remember, this works if it works for numbers, right? One number or expression equal to another expression, and then that expression equal to a third expression, 1 and 3 congruent to one another, equal to one another. If that's true for numbers, it also works for shapes, right? It's also going to work for shapes in this instance. It doesn't always work. If it works for numbers, it doesn't always work for shapes, but this one it does. But we just call it congruency. Anyways, take like 30 seconds to finish this up. It's only 4, so probably already done it already. Take 30 seconds. Ready, set, go. $20 seconds. Did we watch the Celtics-Miami Heat game tonight? I'm missing the Clippers game. Game 7. 8 seconds. Give it a shot. 3, 2, and 1. All right, we're back on it. We're going to get our answers. We'll just go over it very quickly. I'm meant to have a ready, set, go. Too late. I was going to be like, too late. You just need to jump into it. Ready, set, go. Anyways, this is dumb humor anyways. Here are the answers. All right, so check it out here. Hopefully you got them all. You're checking your answers. If not, you're going back and rewatching it, or just going back and looking at it and trying it on your own if you haven't tried already. So this has an and. Look, there's no if here. So interesting. So they're using reflexive property twice here, that any figure is congruent to itself. So it's the same thing mentioned in both congruency statements. Boom, reflexive property. We look back on ourselves, reflecting. We reflect on ourselves, right? We're the same person as we are. I don't know, getting too philosophical here. Symmetric, right? So this is just sides of the congruency symbols changing. Angle DEG congruent to angle BAC. That's the same thing as saying angle BAC is congruent to angle DEG. So we're good to go. And then, yeah, this is probably easier right here, especially after you did the congruency stuff earlier. So let me know if you have questions on that. All right, part 3 of today's lesson. We went through the first 2. I think we're doing a little better on time. Again, I'm trying to get these a little bit faster. I'm trying to give you what I think maybe like 10 to 15 people need, which is kind of like a lot of kind of details here. I think more people need that, but 10 to 15 people will watch this and get a decent amount out of it and be kind of ahead. So I appreciate you for sitting there and watching this right here. I think it's definitely the right thing to do. Okay, this is the first proof we're going to do. So in part 3 of today's lesson in the final thing of today's lesson is we're actually going to just practice some geometry proofs. So you've seen what algebra proofs look like in terms of starting with a given premise, and those were equations, and then using all those properties of equality and distributive property of multiplication over division, right? Or sorry, over addition. So using those properties to prove a fact about that equation, like what does x have to equal, for instance. So those were examples you did on Monday of how to prove facts in algebra. One of the ways to prove facts in algebra. What you're doing now is you're going to prove facts in geometry. So what we have in front of you here is kind of what a proof's going to look like in geometry. And this is a very basic one. This one isn't mind-blowing, but it is a fact that we're going to prove about this particular diagram. Okay, so here, what we call this right here is the given diagram. It's what's given to us by the math gods or Mr. Fortin. This is our given diagram. So this is kind of our situation we find ourselves in. It's given to us from the math gods. We got a diagram here. We got segment RT. We got 7PQ. It looks like it intersects at S. So sometimes they'll tell you all that information, but I'm actually going to cross it out right here because that's not that important. Like if you see something clearly in a diagram, you don't actually need to be told it in this actually written given right here. So kind of ignore that on this particular problem because here are our givens, our given premises of the problem. We have our given diagram, and then right here, this is our given premises of this particular proof. Okay, so this is given premise. We start with this diagram where we have these two segments crossing over one another, and what we know beyond what's shown in the diagram is that RS is equal to PS. That means length RS is equal to length PS. Remember, those are numbers, but that is not going to matter in this problem here. So PS and RS up here, notice here. So this part of the larger segment and this part of the larger segment are congruent, but they say their lengths are equal to one another. It doesn't really matter whether it's talking about lengths or congruency. It's fine. You can use these tick marks here. Second thing, second fact that's given to us at the beginning. Remember, the given premises are facts about the problem that are given to you by the math gods. Is that ST is the same length as SQ. So those two things here. Okay, so check this out here. This is gonna be a really easy thing to prove because the thing we have to prove here is given that we have this small segment and this small segment, they're the same lengths. And then we have this, and I'll put 2 for 2 tick marks down here. This like larger, but still kind of small segments, and this larger of the two small segments, the larger of the two, that those two have the same lengths here. The goal here is what we want to do is we want to prove, that RT, will we know that this whole length here, will we know that it's going to be the same length as this whole thing here, PQ, right? PQ right here. And you might look at it and be like, well, obviously, but how could you justify it? What are the rules, definitions, and maybe previously proven facts that can help prove this here, which is this fact, that RT equals PQ, okay? And that's what we're gonna do right now. I'm gonna kind of skip over a lot of these things here because this is all just kind of a refresher on this, but hopefully you read it when you're looking at the slides here. And let's go ahead and do our first geometry proof. Hey, it's not really that interesting of a one, but at least it'll be something we can do together. And we'll get to interesting ones later about all these crazy relationships that exist with shapes here. So now it's time to prove geometric proofs. Below is the first proof, right together. Excellent, for geometry. We've written other proofs, but this is finally a geometry proof when we write together. Check it out here. So this is going to work kind of exactly like you've done for the algebra, right? The algebra stuff you've done the other day. So statements on the left side, that's going to be kind of where your math's going to go. So these are definitely statements we're going to use, okay? Because those are our given premises. And then reasons are going to be the justification for why you are writing the reason you're writing, okay? How do I know it, okay? See what I'm saying? I think you have an idea of where to start. So remember, when you're doing equations, what did you start with? What was your first step? When you start with an equation, you want to prove something about it. Well, you got to tell me what the equation is. So just like that, you want to start with your given premise. This is like 90% of the time, this is going to be your first step. So this should be very easy to you by now about how to start a proof. And that's the first thing. This is a semicolon right here. This is the second thing. That looks like a less than symbol, so I'm going to get rid of that real quick so as to hopefully not confuse you guys. Sorry, I'm on my stylus here. So RS is equal to PS. That was the premise number one, semicolon in between, just like going to separate our statements here that were given to us. And then ST equals SQ. Again, it does the thing where it doesn't look like an equals sign. Reason, why am I allowed to say that this is true, right? This is, what do I know? I know this. Why am I allowed to say that this is true? Well, it's our given premise. All right, there's step one, okay? Step one is you're going to say given. Sorry, it's ugly, but I wrote given right there. Step two, so now we need to figure out, now we need to use all these postulates and definitions and other things we realize, other things we can say, properties from algebra, to start saying more things here. So in algebra, you start with an equation and then you start doing stuff to that equation to modify it here. So you could think, what can I do to modify this right now? Or, so you can kind of think about what you can modify this right now. I'm going to hold on to that thought for a second. Or you can think about what it is I'm trying to prove. So again, what you're trying to do in a proof is you're trying to get to here. So usually in my second step, I write my givens down and then I ask myself, right, what do I need to prove? And we need to prove, right, RT equals PQ. Ugly, but that says we need to prove RT equals PQ. So the question is, guys, look at this here, the given. Does the given say anything about RT or PQ? Is RT or PQ into the proof yet? Into the proof yet? Because if it were an equation, right, we could maybe manipulate an equation and get to RT equals PQ. Have we said anything about RT or PQ yet? No, we haven't actually said about anything about RT or PQ. So question, what's maybe one way I can get RT? Okay, how would I get the statement, something, say something about length RT and something about about length PQ, because the idea is we want to get those two things, show that those lengths are the same here. What's one thing I can maybe, so let me just chunk it a little bit together. What's one thing I can say about RT that's going to allow me to start talking about RT in the proof? I'll put hints. I'll put RT right here. What do we know about RT? Well, we're trying to get it to be equal to PQ. Forget about PQ for a second, but what do we know about RT? Well, what we know about RT is that RS plus ST equals RT. So here, what did we do there? RS plus ST. So we did part plus part equals the whole segment. Do you guys remember what reason this is here? We added this the length of a small segment to the length of the next small segment here, and that equaled the length of the whole segment right there. The whole segment right there. So that is what? Is that a definition or is that a postulate? That's a postulate. So here, segment addition postulate. So now I have, okay, I wrote segment addition postulate right there. Sorry, that's so messy. So now I have something, I have RT in my proof. Can I get PQ in there? Sure, I can do segment addition postulate as well. So I can do PS plus SQ equals PQ. Reason? Well, it's also the segment addition postulate. So I'm going to leave that as one reason on this particular proof, right? These two statements right here are segment addition postulate. Okay, step 3, right? Step 3. So now we got RT, we got RT and PQ. We got to show that PQ actually equals RT. So this might be the hardest step of the proof right here. RT, how can we show that RT equals PQ? Well, what do we notice here? Well, RS plus ST, and we have PS plus SQ, right? Those equal the two lengths right here. But what else do we know about PS plus SQ and RS plus ST? They would have to equal each other here. So I'm going to write it down right here, and maybe you write this down, and then you think about what the reason is afterwards here. So RS plus RT equals PS plus SQ. Okay? So obviously we can logically kind of see that right there, but what's actually going to be the reason that we're able to do this right here? Who's going to just yell it out in class right here? Well, this would actually be the addition property of equality. Okay, from step 1. Look at this right here. So this is oftentimes things. Addition property equality, a lot of times when you have 4 different things being said here, RS equals PS, so that's a statement of equality. You have another statement of equality, RT equaling to SQ. So what did you do going from step 1 to step 3? Well, we added the left sides together. Look at this here, RS plus ST, that's right here, and we added the right sides together. Right? We added the right sides together. I might do that in a different color so you can see what I'm talking about. That RS plus ST, if we're adding an equal thing to the left side of this, and the thing that this thing was equal to, we're adding an equal thing to the right side of this equation, okay? What we get as a result, if we added both of those two together, we would get this statement right here, So interestingly enough, addition property of equality, we built that off of step 1. So this is going to be one of the harder things, and one of the differences between geometry proofs and algebra proofs is that sometimes you're talking about previous steps in order to get a step later into the future. So anyways, addition property equality is what you need to know for now. So now we have this, we have RS plus ST equals PS plus SQ, and this is really good because actually we're going to be able to finish the proof in the next step. And the reason why I'm going so slowly on this is because it's the first time, and you just need to see practice, and I'll show you examples that are a lot faster after this here, I promise. Step 4. Okay, step 4 is actually how we're going to finish it. So we're going to finish it because we're actually going to say this right here. So let me switch to that color. All right, it's orange right here. We're going to finish our proof by saying that RT equals PQ. Why am I allowed to say that right now at this point in time? Well, what do we know about RT? It equals what? It equals RS plus ST. Where is RS plus ST? It's right there. It's an expression, the left side of this equal sign. And what do we know about PQ? Oh, it equals what appears on the other side of this equals right here. We got an equals right there. Check it out. So what we're doing is we're putting PQ in here, and we're putting RT in here. How many things are getting talked about? We have an expression here, expression 1, expression 2, going into a third expression that's equal to, and then we have a fourth expression going into this where this one's going into the fourth one here. So this here is going to be a little bit tricky because because, hey, you're going to want to stay transitive potentially in this one. But how many things were we being talked about there? 4 things, not 3. So this is actually the substitution property of equality. You'll see why this is substitution, not transitive, when you get more practice. So substitution prop of equality. Super messy, super messy. So I actually have the answer on the next slide, and we'll talk about it a little bit more. And here's really where it slows down. We did the first 20 slides and very quickly. When we get to the proofs, they take a lot longer. Okay, this is just a little bit more clearly laid out right here. Just to reiterate, the first step is pretty much always going to be your givens, right? Always going to be your givens. Then, right, the way what I'd recommend, and again, I'm going to break this down. I'll write it down as steps for you a little bit later, maybe in section 1.8. Then I would look to what you need to prove. Figure out how I can say something about RT. Is there anything I can say about RT? Well, yeah, RT, what we know about RT is that RS plus ST equals RT. That's the segment addition postulate. Same thing too, we can get PQ into this proof by doing PS plus SQ, and that equals PQ. That's also the segment addition postulate. Part plus part equals whole. And then, right, then the goal becomes, well, now I have this being said right here, right? I have this action right here, right there, right? We got that, and right, we know that this and this are equal to these 2 things here. So is there a way we can say that and that equal each other? Well, yes, there were, right? We could take ST right here and add it. I'm doing this, and you're not going to see it because this is a picture, not something I can draw on. And I do plus SQ over here, then I got these 2 things right there. That's the addition property of equality from step 1. And then finally, because RT equals RS plus ST, substitute RT right here. Because PQ equals PS plus SQ, substitute PQ right there. Boom, bada bing, bada boom. That was really lame. I apologize for that. Given this situation, we know that this is true right now. And we've proven a fact about that diagram. Facts are usually are a dime a dozen, right? They come up a lot. Facts are everywhere in the world. Some are really important, like the Pythagorean theorem is an important fact in geometry. Other ones less important. This one was just to see a proof, because you're going to be doing stuff like this for homework in the next 2 days here. All right. So anyways, just to point out here, stating kind of the obvious, right? Because I remember when I was a geometry student, I was like, what do I start with? I got to do what? And it was like, do your given, right? First step should be given in your proof. Like 90% of the time, it's going to be just writing your givens, and then doing little things like thinking about what you're ending with and figuring out a way to you put something that you're ending with in there. Anyways, then the other silly thing where I was like in geometry in high school, like it was like a month or 2 being like, when am I done with my proofs? I never know when I'm done. You're done with your proof when you get to the proof there. So sort of stating the obvious, once you string together these reasons together, and if you're able to say this, which is fully justified by all the steps that have happened so far. There's a reason for every sort of manipulation you're doing right now. If you can, so starting with this as a given, and then you're stringing together other logical statements, if you can get, once you say this thing that's in the proof section right here, once you say it in the proof, your proof is done. You've proven your facts, right? You're proving your facts. And then we know that this is true, right? This is I'll say more about this as we go a little later, but you've proven a fact because you've done all the work. We have the proof for it. So now in the future, when you have a diagram like this, and you know that that's congruent to this, and then that's congruent to that, and they're crossing each other, the thing you can just conclude right away, because we've already proven it, is that we know, because we've written a proof for it, we deduced it, that RT, that the whole segments also need to be congruent to one another as well, or their lengths need to be equal. All right, so that was sort of the long one for you. We'll do some quicker ones in a second, but I just wanted to point out too some of the things we used in that one and other things you'll see in proofs as well. So just wanted to point out that you use properties of algebra, right? This section is called properties of algebra. You use them in a lot of the proofs tonight for homework. You also used a postulate in the last theorem. We also used a postulate in the last theorem, right? The segment addition postulate. So remember, there are properties from algebra, there are rules like postulates, and then there are also definitions. We've learned a whole bunch of definitions already, and those are also going to be used in proofs. I don't think they'll be used in the proof in the homework tonight, but in section 1.5, they'll definitely be used in those proofs without a doubt here. So for instance, definition of midpoint, right? So a lot of the definitions we've learned so far are facts, not facts. They're definitions, they're descriptions that we all agree to about particular features or shapes. So if we know we have a midpoint in a diagram, the thing we're able to deduce, the thing we're able to say about that, what that midpoint does is that, hey, boom, we don't just have a midpoint, we have 2 congruent segments that we can say here. And remember, definitions, if we know that this, for instance, segment AC is congruent to segment CB, and A, B, and C are all collinear, right? A, B, and C, A, C, and B, and we know that AC and BC are congruent, we would also be able to make the conclusion that C is the midpoint of segment AB, and that would be a way we can use definition. Anyways, definitions are double-sided arrows. I've said that a few times right now. That'll be important coming later. Not today, but anyways, a definition will come up in this one too. Proof example number 2. Okay, so check this one out here. Given C is the midpoint of segment AB, let's do it together. Let's do it nice and quick. Statement number 1, what am I going to write? Well, I'm going to write that C is the midpoint of AB, because we start with our 90% of the time, what's your first step in a proof? It's the what? The given. All right, next step. Who's got my next step? Going once, going twice. I don't have much space for this one right here. Step 2. All right, so I got to say something about AB at some point. It's segment AB. Okay, I can say something about that. I got to say something about BC at some point. So let's get saying something about, let's get actually not about AC. Let's get something about saying something about BC. I can think about something we can say about BC. Well, I can use this. C is the midpoint of AB. So one thing I can actually use is use the definition of midpoint. So I can say that BC equals AC. That's one way we can use a definition in a proof. Okay, I got definition of midpoint here. Step 3. So now I got BC into my proof right here. I also got to get AB. Okay, get AB. So how can I start talking about AB? Because I want to prove something about AB. I want to prove that AB is equal to twice this. I've already proven that BC is congruent to AC because C is a midpoint. So that's good. But I want to see twice this length equals AB. This will actually be a theorem that we'll have in the next section because it just saves some time in other proofs. Anyways, what can I say about AB? Well, I can do what I did in the last slide. I can do segment addition postulate. So I can do AC plus BC equals AB. And that's segment addition postulate. Step 4. Okay, step 4 right here. So now I got AB right here. I got BC right here. My goal is I want to get 2BC. Okay, 2BC right here. I have BC right here, but I got to add AC to it, and that's what's equal to AB right here, okay? So question, what can I do? What can I do? Well, it looks like we're doing the substitution property of equality again here. Yes, because what we're doing in this one here, this should be clearly substitution, not transitive, because what we need to do right here is we don't want to say AC plus BC equals AB. We actually want to take this BC and place it right in there for AC right here, because BC plus AC, not plus AC, sorry, BC equals AC, right? Look at this here, BC equals AC. So since BC is the same thing as AC, we can replace that in an equation here. So we can take BC, substitute it with AC right here, and all of a sudden I got BC, but then, right, I'm rewriting this equation up here, BC plus BC equals AB. More importantly is I can combine like terms right now. Look at this here. This means 2 times length BC, right? That's how we'd say that out loud. 2 times BC here. So BC plus BC, right? We're adding the same thing with one another. So shorthand for that is multiplication. So 2BC equals AB. And we have gotten to what we wanted to prove. Because we have 2BC equal to AB up here. We could do the symmetric property if we wanted to. If we wanted to present it exactly like this. But remember, I said symmetric property doesn't matter. Anyways, step 4, what justifies this? What did we do here? Again, you don't have to say combine like terms. But again, what we did from step 2 and 3 is we substituted what BC was equal to, what AC was equal to, which is BC. We put that BC into AC right here. So we did substitution, step 2 into step 3. And that is our second proof we've done, proof example number 2. And we can look at it a little bit more clearly right here. Any questions on that one? Maybe rewatch it. Maybe read this on your own time. I'm not going to go over this one. I think you guys probably want to do your exit ticket. Move on with your merry lives right here. Proof example number 3. I think this is actually the last one. Guys, usually I do 4 examples when I do this lesson. So you're saving one. You're missing out on one, actually. But just I wanted to show you this one here and end on this one because I know these videos are a lot tougher than doing this in class. And also your homework tonight is really just going to have fill in the blank proofs. So there's actually reasons are going to be missing. And you have to fill them in here, okay? What have I been telling you all along? Step 1, what's the thing we're gonna do step 1? What do we put first? Well, step 1 is this, okay? It's our given premise. Remember, given diagram, given premise beyond the diagram. A fact about that diagram is though that measure of angle AOC, Alexandria Ocasio-Cortez, is equal to measure of angle BOD. That doesn't work here. But Barack Obama, D, I don't know what D stands for. Anyways, given premise. All right. Step 2, angle addition postulate. All right. So anyways, I got to say something about measure of angle 1, measure of angle 3 at some point. So let's check out exactly what we're trying to prove. So the measure of angle 3 is angle COD. And it looks like we know we're being told that AOC here, AOC and BOD are equal to, the measurements are equal to each other. Therefore, they're congruent. But anyways, angle addition postulate is the next step here. So my guess is here, I want to say something about measure of angle 3 at some point. I also want to say something about measure of angle 1. So my guess is that we got to do measure of angle 1 plus measure of angle 2 equals angle AOC. And measure of angle 3 plus measure of angle 2 equals measure of angle BOD. Okay, so then we're talking about something in step 1. A really good step of a proof is when you're talking about stuff that came earlier and then is also going to come later, which is this right here. So check it out here. What I can say this, angle addition postulate, what will really help me here is if I say measure of angle 1. That's good because that's going to be in my conclusions. Now I got it into the proof plus measure of angle 2. That equals measure of angle AOC. And then I have measure of angle 3 plus measure of angle 2, right? Measure of angle 3 plus measure of angle 2 equals measure of angle BOD. All right, and very nice, because what do we know about measure of angle 2 and measure of angle 2? Well, they equal each other because of reflexive, okay? You're actually going to use that later. And then here, measure of angle AOC and measure of angle BOD, that was actually our given. Check it out. That was our given right here. So we know that measure of angle AOC and measure of angle BOD, they equal each other. So actually, what can we say about this and this? Those two expressions equal these things, so they're going to equal each other. Okay, going to equal each other here. So this is a tricky thing here is that you got to count up how many different things are being said right now. We have an expression here, an expression number 1 equal to an expression number 2 right here. And then we have number 3 congruent to an expression number 4 right here. And 2 and 4 are congruent. What can we conclude about 1 and 3? They would also have to be equal as well. Sorry, it's an equal sign right there. So this is tricky because there are 4 things being said split across 2 equations. So this is going to be substitution. An example of substitution. Substitution is a lot more lenient than Euclid's good old common notion number 1, the transitive property. It's a lot more lenient. So there are a lot of different ways you're going to see substitution. This is one of them here. The idea about this one is that what you're doing, because this equals measure of angle AOC, you're taking this and you're popping it in, right? Measure of angle 1 plus measure of angle 2 is where measure of angle AOC is. And then here, measure of angle 3 plus measure of angle 2, that's where measure of angle BOD is here. So you're actually taking this and substituting this into an existing equation. Okay, that's the difference between that and transitive. Transitive, you're kind of making it, you're deducing something by creating a new statement that's based on the 2 previous statements here. Anyways, tons of time to practice that later. You don't really have to use reflexive in this situation. A lot of times what you can do is just subtract the measure of angle 2 and measure of angle 2 from both sides. So we've justified step 3. Our whole goal is we want to get measure of angle 1 equaling measure of angle 3, and we can do that. Because measure of angle 1, we're adding something to it here. Measure of angle 3, we're adding the same thing over here. So what we can do is we can subtract measure of angle 2 from this side and subtract measure of angle 2 from this side. So remember, measure of angle 2 is a number, right? It's an angle measurement. It's somewhere between 0 and 180. It's a real number. So we're just subtracting 2 equal numbers, right? The same thing, subtracting them from one another. From both sides of an equation. So what that is, if we're subtracting one thing and we're subtracting the same thing or an equal thing from the other side of the equation, the reason why we're allowed to do this is we have a rule called the subtraction property of equality, okay? And that's how we're going to get to our final answer. We've proven our third fact of the day, which again is not that useful, but when we have a diagram like this, if, right, we know that these 2 angles, right? It's not the 2 angles. This angle here that kind of contains angle 2 and angle 3, and this angle right here, AOC, if we know those 2 angles have the same measurements, okay, we know that angle 2 is congruent to itself and has the same measurement to itself. So therefore, we're able to confirm, right? We know for sure this angle over here and that angle here over here, these little ones here, AOB and COD, have to be congruent to one another, or equal measurements. Anyways, it's all kind of confusing. You just got to practice. It's all good. And here's an example of this in case you couldn't follow my writing. We're having a little bit of trouble with it. So we'll keep on going here. All right. Why I need to take good notes. And look at this. We're at slide 29. Man, we went through so much stuff, but we're good to go. So just reminders, guys, taking notes is critical in this course, right? This is a super important course to take notes. I don't really have my algebra students, algebra 1 students, take very many notes. I tell them they should be writing stuff down on the whiteboard. And, notes are not that important in Algebra 1. You will do better if you take notes in Algebra 1. But in geometry, you have to take notes, right? This is too much stuff, right? Too much stuff just to be reading and be like, I kind of got that. Like, I'll get it later. No, you're going to forget it because you're going to break this stuff out, right? What is the subtraction property of equality? When you have a situation where things are being subtracted, it might be subtraction property. It might be something different. Okay, so there's a lot of stuff already, guys. So one thing that I like to say, the math standard that's sort of biggest in geometry is being organized, right? We have a whole standard around being organized. I forget the exact wording of it, but organization is super, super important. So this list is only really going to grow because we're going to start proving, we're going to use these original assumptions here, like the angle addition postulate and the properties from algebra and some shapes that we have. We're going to get facts proven of those, right? We're going to take these assumptions and from that, we're going to deduce things from them that are going to be facts, and this list will only grow for things that we can prove that we know are universally true, which is a very exciting thing, but you got to be organized. You got to be writing this stuff down, highlight down, right? Every definition you get, highlight it, or every fact you get, which is called a theorem, right? Highlight that. Every postulate, highlight that because you're going to use them into proofs, okay? I'm not going to give you lists like this in the future, not at all, so you got to keep up. You got to take your notes here. Let's do one from Thursday's homework right now, shall we? Boom, we got this one here. We can do this one quickly, right? This is going to be on your Thursday homework. So if you're still watching, gravy. You're getting gravy right here. If not, like whatever, you watch this before you do the homework on Thursday. Classroom exercise number 11, page 19. So check it out here. This is actually probably a pretty similar one to what we just did right here. All right, step 1, list out your givens. Okay, it's like less important to understand what this proof is, like what it's trying to prove. It's just more important that you just get used to the systems, the logic of it all here. Start with your givens. So it looks like we have this angle equal to that angle. The measurements are equal. This measurement equal to that measurement right here. Our goal is we want to get the holes, right? This angle, congruence, to this larger angle right here, FED or DEF right here, okay? Can we prove this one? Heck yeah, we can definitely prove it. So first step is usually I think about what I can get measure of angle ABC or measure of angle DEF into the proof. I usually like doing that step 2. They didn't do that. They waited on that here. So anyways, what I would have done step 2 is this. Step 3, what justifies measure of angle 1 plus measure of angle 2 equals measure of angle ABF? Well, this is a part plus part equals whole assumption right here. That is the angle addition postulate. Okay, so I'm going to fill that one in. Angle addition postulate. So they said something before that too. Okay, this is going to go through the structure. We've seen ones like this, but for segments here, this is very similar, which I can see right now. But anyways, so what did they do here? Well, they wanted to talk about this, which is part of the angle addition postulate. Measure of angle 1 plus measure of angle 2. We can actually confirm that that's equal to measure of angle 3 plus measure of angle 4 because, right? What do we do here? We had 2 equal things here, right? 2 equaled 4, so we can add 2 to the left side of this equation up here. Measure of angle 1 plus measure of angle 2 would have to equal the right side of an equation added to this right side of the equation because it's equal to that. So we add measure of angle 3 plus measure of angle 4, boom, we get this statement right here. So what we did is we manipulated this right here, added equal things to both sides, and we created a new equation right there. We know it's valid because of the addition property of equality. Finally, wrapping this one up for your homework, guys. Your homework's not going to be too bad. It's going to be a lot of reading and letters and words, but it's fine, right? You get done this in 2 minutes. And measure of angle ABC is congruent to measure of angle DEF. Why can I make that statement? Well, hey, I can make that statement because I know that measure of angle ABC equals this. And I have this up here, so I can take this, substitute it for the left side of the equation right here. So that's right here. That's now on the left side of the equation right here. And then I can take this right here, DEF, okay, equals that right there. And that's on the right side of the equation right here. So I can take measure of angle DEF, put it in the right side of the equation there. I get this right here. And that, my friends, is what we were trying to prove right here. And the reason why I was able to do that going from step 3 to step 4 is that I substituted this information from step 3 to step 2. So this is the substitution property, not transitive, because you're talking about 4 expressions, not 3, not 2 things that are each equal to the same thing. We have 2 things, they're equal to different things, but those 2 things are equal to each other. Anyways, go with substitution on that one, not transitive. And that's that for me. Hopefully you stuck it out and watched the whole thing. I think you'll do better. You probably feel more confident on Thursday's classwork. If not, it could go okay. I'll give you feedback on your exit ticket. Okay, so it is Wednesday today, so you're doing your exit ticket after this, turning that in, so I can give you feedback on that, hopefully before Thursday's class, and then Thursday you're doing the homework in the textbook. I don't think I have that written out now, but maybe you can find it on Google Classroom and even get started after the exit ticket if you want to. Thanks so much, guys. I will talk to you guys soon. Bye.
I want you to